Next, let's look at the energy that's associated with this electromagnetic wave. Now, in classical wave theory, we know that the amplitude of the wave is related to the energy of the wave. The bigger the amplitude, the more energy the wave carries. The smaller the amplitude, the less energy it carries. And we expect the same to be true here. The amplitudes that we're looking at are the amplitudes of the electric fields and the amplitudes of the magnetic fields. Those are going to determine how much energy this wave is going to be carrying. So if we wanted to calculate the energy density at any point in space and at a given instant in time, we would calculate it from this expression here. This is the energy density. It's 1/2 times the electric constant times the electric field amplitude at a given point in space and time squared plus 1/2 times 1 over the magnetic constant times the magnetic field amplitude squared at a given point in space and time. Now that's the expression for the electromagnetic wave energy. If we had a monochromatic wave, like we talked about at the very beginning, that was our sort of easy trial solution we looked at, we saw in that particular case that the electric field vector was related to the magnetic field vector by just a proportionality constant, which was the speed of light. So we can actually use this to get a simpler expression for the energy for monochromatic waves, since we can substitute in, eliminate B from this expression, and we can get this. And that tells us the energy density for a monochromatic wave. We can go further, and we can take the analytical wave function, and we can plug it into this expression, and we'll plug it in and square it. And then if we integrate it over one cycle of this cosine argument, so in other words, from when this argument goes from 0 to 2 pi, the integral over that is going to give us the average energy density for a monochromatic plane wave, which is given simply by the amplitude of the electric field squared. All right, so that's probably no surprise given what we know from classical waves. And this is the result we get for a monochromatic wave, plane wave. But if you wanted to be more general, you can always go back to this expression up here. Now, the energy that's flowing with this electromagnetic wave is moving along the propagation direction. So it's moving along the k direction. And even though the energy comes from the amplitude of the E field and the B field, the energy is being transported along k. And we can create a vector called the pointing vector, whose length is the energy that's being transferred, being moved, and the direction of this vector is the direction in which that energy is flowing. So we can construct that vector, the pointing vector, named after a guy named Poynting, where it's the cross product of E and B divided by the magnetic constant, and that gives us the energy per unit time per unit area, or the power per unit area that's flowing in that as that wave propagates through space along a given direction. Now, for a monochromatic plane wave, we can take our previous arguments and we can use those to find that actually averaged over one cycle, the average pointing vector is going to be just C naught times the energy density times the unit vector along the direction in which the wave is propagating. Now, when you're in the lab and you're doing measurements of light intensity, what you're measuring actually is just the magnitude of this pointing vector. So if you're measuring light, the intensity of light coming off some source from at a particular point in space, then you're measuring the magnitude of this vector, and that's just given by this part that's multiplying the EK, the unit vector. So that's this expression right here. So the next part of this chapter, or the last part of this chapter, we're going to look at the radiation that's associated with oscillating dipoles. Now, we've been talking a lot about electromagnetic waves and their behavior, but we haven't really talked much about how you generate them. And probably the simplest way to generate them is through an oscillating electric dipole. So if you see sort of a typical antenna that you might have, a tower, that's just essentially a giant oscillating dipole that's radiating out radio waves or microwaves out into the area. The same will be true for a molecule. If a molecule has an electric dipole moment and it's oscillating, as a function of time, it's changing the dipole moment, then that will also generate electromagnetic waves. So let's look at the general expression for an oscillating electric dipole. So I'm going to take an example, say, that might correspond to, say, a vibrating electric dipole. So a molecule like HCl that's vibrating like this. So we would place the HCl molecule with the bond along the z-axis and let it vibrate, and we would have a dipole moment that would look something like this as a function of time. So say it's got a cosine modulation, it's oscillating along the d direction, and mu d is just the size of the dipole moment for that molecule. Right. Now, I'm not going to derive what the electric field, magnetic field that's generated by this dipole. I'm just going to give you the result. So if you want to, you can dig further and find out how this result is derived. I'm just going to show you what this result looks like, and then we're going to talk about sort of how the energy flows out of this dipole. So from this dipole, which we've oriented along the z-axis, so it's an oscillating dipole along the z-axis, the electric field at any point in space away from that oscillating dipole is going to be given by this expression here. So let's look at this very carefully. First of all, I'm describing this in terms of spherical unit vectors. So in other words, the dipole is here at the origin, it's oscillating up and down, and I'm looking at the electric field at any point in space around it using spherical unit vectors to describe what's going on. So the electric field then is going to be equal to some magnetic constant over 4 pi, the size of the dipole moment that's oscillating, the oscillating frequency, so it's oscillating at omega, and so it's going to show up here as an omega squared. And then we're going to have a sine theta over r dependence. So r is how far away we are from the origin where the dipole is, and theta is the angle between the z-axis and where you're detecting this electric field. So remember, the dipole is oscillating along z, so if you're at 45 degrees away from z, then that's what that theta corresponds to, the angle away from z. And then here we have the oscillation of the electric field due to this oscillation, and you'll notice that it has the same time dependence, omega times t, but it's actually delayed by some amount, r over c, because it takes time for light to travel from the origin out to that point in space where we're actually detecting the oscillating electric field. So the electric field is oscillating along the unit vector along theta, and the magnetic field, which has a very similar expression here, except it's divided by the speed of light here, is oscillating perpendicular to that along the unit vector along phi. And this is what we get. Now, you'll notice that there is these are what we call spherical waves that are radiating out from the origin for this dipole, and that they fall off in amplitude as 1 over r. So as you get further and further away, the amplitude of the electric field and the magnetic field fall as 1 over r. So that's what you would expect, for example, if you're moving away from your cell tower and you're trying to get signal, you expect the electric fields that you're going to be experiencing from that are going to be falling as 1 over r. And actually, when you get far enough away, then these spherical waves, as you get far enough away, and we saw this in the wave chapter, they'll start to look more and more like plane waves. They'll start to flatten out as you get far enough away from them. Now, the energy is what we're interested in really here, is to see how is the energy of this dipole being radiated away, and that is just going to be the Poynting vector. So we're going to take the electric field and the magnetic field at any point in space, and we're going to calculate the Poynting vector. So we're going to use those two solutions on the previous page here, and we're going to plug them into this expression, and we're going to get this expression here, and now we get a term that is pointing along the direction r, which is the radially out from the dipole at the origin. Then the energy is flowing out along the r unit vector, and this is the size of that energy, and you can see it's oscillating in time, and it has this dependence of 1 over r squared, because the whole thing is squared, and sine squared here. So if we average over one oscillator cycle like we did before, then this whole thing simplifies to this. So this is the average energy, and what you get is that we have 1 over r squared sine squared theta and then we have the power that's coming out along R. So from the origin out here is how the power is radiating out. So one of the things you notice is that when sine theta is equal to 0, this whole expression goes to 0. So if your dipole is oscillating along z-axis and you're sitting up here above it on the z-axis, you're not going to see any power being emitted out towards you. But if you're out here along the x and y, where theta is equal to 90 degrees, then that's where you're going to get the maximum amplitude, the maximum intensity of energy coming out towards you there. So what this profile looks like actually is looks like a donut. So in other words, the whole, the z-axis goes through the whole of the donut, and then in the xy plane is the rest of the energy moving like the donut. So if you actually integrate over the entire sphere, so the whole energy that's being radiated, integrate over, over all theta and phi, then you find that the energy coming off this dipole is just going to be given by this expression here. So it's the dipole squared times the frequency to the fourth power divided by the speed of light with these other constants here. So I have this nice picture here. I stole it out of a nice book called The Student Guide to Waves. And what you see here is a picture of the electric field lines that are at an instant in time emanating away emanating away from this electric dipole moment that's oscillating along z. So here's the z-axis here. It's oscillating this way. So as you see, if you're just directly above the oscillating dipole along the z-axis, there's no E field up here or down here, and the E field is strongest out here along the x and in the xy plane here. So this, you imagine this just being rotated around, and that's the donut of electric field that you see from this oscillating dipole. And of course, as you get further and further out, and this picture here takes you further out, you start to see that these waves coming off, these spherical waves, start to flatten out a bit, and you start getting something that looks more and more like a plane wave here. And this is one of the reasons why, for example, like when I was a kid and I had a walkie-talkie, I would have a little radio, and you have an antenna, telescopic antenna, and if you want to talk to somebody else who has another walkie-talkie, you would hold the antenna up like this, and you would talk, and they would do the same on their end, and the waves coming off this dipole oscillator would be transmitted, so the energy coming off would be received by them and vice versa. But of course, obviously from this picture, the last thing you want to do is point the antenna directly at them and they put their antenna directly at you, because that's the region here where there's no energy coming off, and so you're not going to get a good signal transmitted between the two of you. So there you learned a little bit about antenna theory in addition here. So that's it for this, and I have also a web app that has some really nice pictures, 3D, where you can rotate them and see what some of these waves look like.